Welcome to the class. Our next unit is radiation quantities, units, and dosimeters. And we will discuss some units, those we are using in measurement of or for quantifying or for describing radiations and their units. We can start with the concept of fluence and flux. This fluence, represented as phi, this is capital letter phi, is the number of photons passing through a unit cross sectional area. And more correctly, you can consider it as the number of photons or particles passing through a unit cross sectional area. And you are writing that phi as photons or particles by area. If dn is the number of particles passing through an area dA, this phi can be written as dn by dA. And since the number has no unit, it is usually expressed in centimeter raised to minus 2 or meter raised to minus 2. And now flux is the fluence rate, and fluence is number of particles passing through unit cross sectional area, and that divided by time will give you flux. So flux is the number of photons or particles passing through a unit cross sectional area per unit time. So this you are writing as small letter phi, this is capital letter phi. Small phi is photons or particles by area into time, that is dn by dA into dt. And here the unit will be centimeter raised to minus 2, second raised to minus 1. And more often, you will represent the quantities in this radiation with CGS units. That is why it is coming with this type quantities. The amount of energy passing through unit cross sectional area is called energy fluence. The number of particles or photons, you have called it as just fluence, and their corresponding energy you can call as the energy fluence. So it is energy by area or dE by dA. And here the unit will be joule per meter square. This is the SI unit. Energy fluence can be calculated from photon or particle fluence by using following relation. You can write psi as energy fluence is psi. Psi is energy by area, that is dE by dA. This dE you can write as dN into E. That means number of particles with energy E. And this dN by dA you can write as phi. That is the fluence. So energy fluence you can write as fluence into energy, where E is the energy of the particle and dN represents the number of particles with the energy E. And activity. Activity refers to the number of unstable nuclei that regain stability through radio disintegration per unit time. That means normally you are writing it as dN by dt. The quantity of radiation released from radioactive material is directly proportional to the activity. Activity gives an idea about the quantity of radiation released per unit time, or you can call it as the disintegration rate from the radiation source. And normally you are considering it as dN by dt. And becquerel, represented as BQ, is the SI unit of activity. You can define as 1 becquerel equal to 1 disintegration per second, that you are writing as dps. So in practice, megabecquerel and gigabecquerel are used as unit. and you can write as 1 megabecquerel is 10 raised to 6 becquerel and 1 gigabecquerel as 10 raised to 9 becquerel. And another unit is curie, that you are writing as Ci. And 1 curie is the number of disintegrations per second from 1 gram of radium, that is your radium 226. And you can get the value as 1 curie is 3.7 into 10 raised to 10 disintegrations per second. And smaller units such as millicurie and microcurie are also used. These are millicurie and microcurie. And relation between curie and becquerel is this 3.7 into 10 raised to 10 disintegration per second, and 1 disintegration per second you can call as becquerel. So this is 1 into 3.7 and raised to 10 disintegration per second. 1 disintegration per second is becquerel. So 1 curie is 3.7 into 10 raised to 10 becquerel. And since activity deals with the nuclear emissions, it does not have any practical application in diagnostic radiology. These units do not tell us the dose delivered to the biological system. Hence, new quantities like exposure and absorbed dose are defined. That means this is the quantity emitted from a source, and those emitted quantities completely will not reach a target. Suppose living things are the target, there will be some loss during its transfer, and the incident radiation will not be completely absorbed, and the effects on the biological system will be based on the quantity absorbed. So this is regarding the source we are defining, but we have to define the quantities regarding the target. That is why we are introducing these new units. So the first unit, or the exposure, was the first quantity, and exposure indicates the amount of ionizing photons present in a field. And the initial definition was you will consider a point and you will consider the unit volume around that. Then we have changed that to unit mass around that. And the number of charged particles produced by ionization is directly proportional to the ionization events. Hence, that means when a charged particle is passing through or interacting with the matter, that charged particle can produce or it can cause ionization. So due to ionization, you will be getting negative and positive charges. So if one photon is passing or interacting with the medium, probability for producing one pair of positive and negative charges. And if 5 numbers are passing, there is a possibility for producing 5. That is why you are saying that the number of charged particles produced by ionization is directly proportional to the ionization events. That means 5 events, 5 charges. Hence, ionizing photons are quantified. That means they are measured based on the basis of total charge produced by them in a given medium. And air is the universal medium to measure exposure. Average minimum energy for photons to produce ionization in air is about 34 electron volt. The first internationally accepted radiation unit was based on the capacity of X-rays or gamma radiations to ionize air, and that process you are calling as exposure. The unit was named roentgen. This is RO and it is represented as capital R. And you can now define roentgen as it is the quantity of ionizing radiation producing ions of one side, this is important, of one side with a charge equal to 2.58 into 10 raised to minus 4 coulomb per kilogram. So your roentgen is the quantity of ionizing radiation producing ions with a charge equal to 2 into 2.58 into 10 raised to minus 4 coulomb per kilogram. And of one side means these ionizing radiations can produce both electrons and positive ions. So you have to consider only with one side. That means either electrons or the positive ions. So if this is the number for one charge, normally it will be double when you consider both the positive and negative charges. So you will be considering only of one side. And there are some difficulties in the unit of roentgen. And they are, it is not a unit of dose, which is a measure of absorbed energy. That means you are considering only the ions produced, that means in air. It can be used only up to photon energy of 3 MeV, and it is defined only for X and gamma radiations in air. So air you are taking as a standard and not on biological systems, etc. And it is defined for photons, the charge produced by photons and not by electrons, protons, heavy charge particles, etc. That you are not considering. And you can see that if you are considering neutrons, they are not producing any ionization. So neutrons are also causing radiation effects. So you can't measure those quantities. So that was, or these are the difficulties in the unit of Roentgen. And next is Kerma. And this Kerma stands for kinetic energy released in the matter. That is KERMA. Kinetic energy released in the matter or kinetic energy released in the material. Both are equivalent terms. And Kerma describe the initial interaction of the photon with an atom in the medium. When X and gamma rays passes through a medium, they transfer kinetic energy to the charged particles, that means electrons and protons, in that medium. And Kerma is the measure of kinetic energy transferred to the charged particles. And you can define this Kerma as the sum of the initial kinetic energy of all the charged ionizing particles liberated by photons in the material of unit mass. That means when these X-rays and gamma rays are passing through a unit mass, they will be giving their energy to protons and electrons, and they will be emitted with a particular kinetic energy. So the initial kinetic energy of all the charged ionizing particles, you have to sum them, and it is known as Kerma. The SI unit of Kerma is joule per kilogram. That means energy per unit mass. And this quantity, joule per kilogram, you are sometimes calling as Gray, GY, simple. And another commonly used unit is RAD. It is radiation absorbed dose. Radiation absorbed dose. That is RAD. And when the reference material is air, the quantity is called air Kerma. And the initial definition for Roentgen was based on air, and this is based on any material. So if it is air, you will be calling this as, that means the sum of initial kinetic energies of all the charged ionizing particle in air. It will be calling as air Kerma. And air Kerma, that means it is actually the unit Gray. So 1 air Kerma you can equivalent to 114 roentgen. This is the relation connecting. And next is exposure to radiation results in the transfer of energy from radiation to the interacting medium. That means energy is transferred to the medium and the energy per unit mass transferred you are considering as Kerma. Transferred energy may not be fully absorbed in the medium because partly it is radiated out in the form of bremsstrahlung. You know this term bremsstrahlung. So it is transferring some energy and that transferring energy you are calling as the Kerma, and from that Kerma some energy, that means when charged particles are they are suffering a deceleration, they may release energy, and that energy you are calling as bremsstrahlung. Hence, and you can see that uh, after that, that particles will be losing their kinetic energy, and that energy may be absorbed by the material itself. But some energy has been released from it in the form of bremsstrahlung. So this Kerma will not be completely absorbed. That means the initial kinetic energy is not completely absorbed in the medium. Some fraction or a small fraction is radiated as bremsstrahlung. Therefore, the absorbed dose is equal to difference between Kerma and the bremsstrahlung loss. So Kerma minus bremsstrahlung loss will be equal to the absorbed dose. Now, a specific definition for this term absorbed dose. The term absorbed dose, you are considering absorbed dose with the letter D, refers to the amount of energy absorbed per unit mass of the substance. So it is energy per unit mass. And the CGS unit you are considering as RAD, which we have already mentioned as radiation absorbed dose. So one rad you are normally defining as 100 erg per gram. So if 100 erg is, so when you a particular radiation is passing through matter, and if you are observing that if 100 gram is absorbed in 1 kilogram, you can say that the absorbed dose is 1 rad. And the unit is independent of the type of radiation and the medium. The definition of roentgen was based on air and based on the particles like X-rays and gamma rays. But here there is no specific mentioning of medium. Any medium will absorb and also any type of radiations. So this unit, that absorbed dose, is independent of type of radiation and the medium. And the SI unit of absorbed dose will be 1 joule per kilogram. So if 1 joule is absorbed per unit mass, you can consider it as 1 gray. And 1 gray SI unit, rad is the older unit, but that will be in the CGS. And now the relation connecting gray and the rad is 1 gray you can write as 1 joule per kilogram, and 1 joule is 10 raised to 7 erg, and 1 kilogram is 10 raised to 3 gram. So 10 raised to 7 by 10 raised to 3 is 10 raised to 4. That will be 10,000 erg per gram. This you can write as 100 into 100 erg per gram. This 100 erg per gram you are calling as rad. This quantity is rad. So this is 100 rad. That means 1 gray is 100 rad. The units rad or gray is defined based on the energy delivered in the medium, and hence it is suitable to describe a biological effect. It is used to quantify the radiation dose to the patient in radiotherapy. That means normally you have to say for a particular treatment, how much gray should be or how much rad should be given to a particular patient. And now roentgen rad conversion factor. The absorbed dose is related to exposure as, actually this is exposure and this is absorbed dose. And this exposure, normally we are considering about the charged or ionization produced, and from that only a part will be normally absorbed, that we have mentioned. So the absorbed dose is related to exposure x as, you are writing as d equal to f into x. This x stands for exposure, d for absorbed dose, and the unit for this dose or absorbed dose is rad, Olden unit, and this x roentgen. That is why you are considering this as this f is the conversion factor. That is why you are considering this f as the roentgen to rad conversion factor. That means you can write as absorbed dose is f into exposure. This f is the roentgen to rad conversion factor. In diagnostic X-ray energies, the F factor for air, muscle and other soft tissue is close to 1. The factor is 4 for bone because of higher photoelectric absorption. And this is an important quantity. Relative biological effectiveness, RBE. All radiations are capable of producing same type of biological effects. That is why they are producing mutation in cells. They can destroy cells, or they can affect the chromosomes in the cell, or they can damage the cell, etc. But the magnitude of the effect per unit dose differs. That means if you have X-rays, gamma rays, electrons, alpha particles, etc., that effect will be different even when the same dose, that means absorbed dose is say 1 gray, but it will be different. In other words, different radiations of equal dose do not produce the same level of biologic response. To evaluate the effectiveness of different radiations, the term relative biological effectiveness, RBE, was introduced. And you can define RBE as dose of 250 kilovolt peak X-rays required to produce certain effect divided by dose of reference radiation required to produce the same effect. That means this, normally you are mentioning the X-rays with the voltage given to them. So if 250 kilovolt peak is given for producing or for accelerating electrons in the X-ray tube, that is the term that 250 kilovolt peak. So the dose of, that means energy absorbed per unit mass, 250 kilovolt per X-rays, how much producing? And if you are using some other type of radiations, the dose of reference radiation required to produce the same effect. This ratio you can call as RBE. And it is found that for X-rays, gamma rays, electrons, etc., if this is X-ray, this ratio will be same. It will be 1. And for X-rays, gamma rays, electrons, etc., this term is nearly 1. And for protons, neutrons, etc., this much dose is not required. So if the terms in the numerator is less, this RB will be greater than 1. And now you can see the RB depends upon the linear energy transfer. LET of the radiation in the medium. It depends on the biological endpoint and the nature of biological system. Biological endpoint means how, that means some cells can retrieve from the dose, and this is normally termed as the biological endpoint. That means the last endpoint of the response. And RB also depends on the total dose and dose rate of radiation. The RB values of different radiations are as follows. For X-rays, gamma rays and electrons it is 1, and for neutrons it is 5 to 50. That means vary with energy and endpoint. So you can have slow electrons, for slow neutrons, fast neutrons, thermal neutrons, etc., etc. And correspondingly this value will vary from 5 to 50. And for protons it is 2, and in some books you can see it as nearly 5, and for heavy particles it is 20. Next is equivalent dose and effective dose. Exposure to radiation may be whole body exposure or partial body exposure. That means it can be uniform or non-uniform exposure. Radio sensitivity of tissues in human body varies towards radiation exposure. Individual tissues contribute differently to the total detriment. Detriment means the state of being harmed or damaged. This term, detriment, is the meaning of health of the exposed person, depending upon the seriousness of the damage and its curability. And equivalent dose, radiation induced biological effects depend not only on the amount of the absorbed dose but also on the parameters like type of radiation and the nature of target, etc. In order to account the above factors, the term radiation weighting factor WR, radiation weighting factor WR, is introduced. It will modify the dose to reflect the relative effectiveness of the type of radiation causing biological damage. The product of the absorbed dose and radiation weighting factor is called equivalent dose, or sometimes dose equivalent. So you can write equivalent dose H as D into WR. So D is the dose, that means energy absorbed per unit mass, and on the type of radiation used you have a term WR. So equivalent dose is absorbed dose into weighting factor. And the weighting factor is 1 for X-rays, gamma rays and electrons of all energies. High linear energy transfer, that LET you have seen. So normally electrons will travel more distance. That means their LET will be small. High LET radiation may cause higher biological effects, hence have higher radiation weighting factor. The radiation weighting factor for various radiations are given. WR we have mentioned photons, that means gamma X-rays 1, electrons 1, neutrons less than 10 keV is 5, and you can see that variation, and protons the value is 5, and for alpha particles it is 20. The SI unit of equivalent dose is sievert, SV, and 1 sievert is 1 gray into WR. Normally this WR has no unit. And roentgen equivalent man is the special unit of equivalent dose when absorbed dose is measured in rad. That means roentgen equivalent man. Here in place of this gray you can use rad. So in that case, this rad, in rad it is correspond to your roentgen, and that roentgen is for air. So if you are considering the biological system, that is why you are considering this as it is the roentgen equivalent to man. So here you have Rad corresponds to roentgen, into you have a weighting factor. So that roentgen you are converting into man, corresponding biological system. That is why it is termed as RUM, not your RUM, it is REM, RUM, roentgen equivalent man, is the special unit of equivalent dose when absorbed dose is measured in rad. And one sievert is 100 RUM, roentgen equivalent man. And next is effective dose. To account for the variation of radiosensitivity of different tissues and the non-uniformity of radiation exposure, the term effective dose is used. The weighting factor of a particular tissue or organ is the risk of stochastic effects. That means the effects which cannot be predicted being induced in the organ when singly irradiated compared to the total risk of inducing stochastic effects if the same radiation dose is received by the whole body. That means if that radiation is received in a particular part or in a whole body, that will be different. And the product of equivalent dose to each tissue irradiated and the corresponding weighting factor of tissue that you are writing as WT. Weighting factor of radiation is also there, and also weighting factor of tissues. It is called effective dose. E equal to WT into H. This H you have written as D into WR. D is the dose. And the SI unit of effective dose is also sievert. This H has the unit sievert. Also E is this H you can write as D into WR. So E is equal to D into WR into WT. And the quantity E expresses the overall measure of health detriment associated with each irradiated tissue as a whole body dose and considers the radiosensitivity of each irradiated tissue. It is used to evaluate the probability of stochastic effects at low doses. So now we have defined first roentgen, then for the dose, the first quantity was dose D. It is energy absorbed per unit mass that you have written as D, and its unit is gray. And then the effectiveness depends on the type of radiation. That is why you have mentioned the equivalent dose, and equivalent dose you are writing as a weighting factor for the type of radiation into dose. So H equal to WR into D or D into WR. And the effective dose, that means the action on the biological system depends on the type of tissues, etc. That is why you have introduced one more term known as the weighting factor of tissue. So this effective dose you are calling as your equivalent dose into weighting factor of tissue. So this D is absorbed dose, this H is equivalent dose, and equivalent dose corresponds to the radiation. And now you have E, which is the effective dose. That means actually what is happening in the cell. And that's all in this class. So from with this we come to an end for the type of quantities or the units commonly we are using in radiation. And in the next class we can deal with the dosimeters. That means how you can measure the radiations. And that's all. Thank you.